Everyone, we're going to be making a video that is pretty conceptual, but towards the end we're going to actually work out a big problem that's going to be really important. This stuff is about alternating currents and impedance. So, if we initially look at a purely resistive circuit, so just a circuit with a resistor, we can see that the current and voltage are in phase. And what that actually means is being in phase is if we draw it out on a little graph here against time. So as we go, the voltage and the current, the maximums and minimums are going to be at the same point in time. So what these lines are showing right here is that the voltage peak and the current peak are both at this specific time. And similarly, the bottoms, the mins are going to be in phase, and they both reach zero, no voltage or no current at the same point in time. And when we compare that to a circuit with just a capacitor, something is different. So in a purely capacitive circuit, the current leads the voltage. So there's actually a trick to kind of remember this, and it's called Eli the Ice Man. So if you remember Eli the Iceman, you'll be able to answer this correctly. So I is going to stand for current, C capacitor. Yeah, let's draw this a little better. L for inductor, and the E for voltage. Okay, so as we have right here, for a capacitive circuit, we have that the current I is coming before E, the voltage. So this is for a capacitor, which is what the C means. I is for current, E is for voltage. So just remember that. And we can see it on this graph right here, actually. For right here, our current I reaches its peak before the voltage does. So right here, when the current is at its peak, the voltage is still increasing. So that's all that means. And it leads the voltage by pi over 2. And what that actually means is 90 degrees. So pi is 180 degrees. Okay. And an important equation relating to this is the reactance. So that's the resistance created by the capacitor. It's measured in ohms. And this is the important equation that you'll have to use. 1 divided by 2 pi f, the frequency, times the capacitance. And again, looking at the inductive circuit, we have this equation here. So the reactance equals 2 pi times the frequency times the inductance. Okay? And the other part of our mnemonic trick is that the voltage, E, leads the current in an inductor, L, and it leads the current. So E comes before I in an inductor. Just like that. Okay? And when we put all these things together into a series RCL circuit, we have that the resistance is actually going to be called something different, called the impedance, which is Z. And the equation for Z is this right here. And depending on what is in the circuit, the impedance will vary. So if it is an RLC or RCL circuit, we have Z. And if we just have a resistor and an inductor, we instead have this. And for this scenario, the phase angle is going to be positive. It's going to be somewhere between 0 degrees and 90 degrees. When we just have a capacitor and a resistor, it's going to be negative. It's going to be between negative 90 and 0 degrees. So that's exactly what this is saying right here. The phase angle can range from negative 90 degrees to positive 90 degrees. Okay. So let's look at a question. So if the phase angle is negative 47 degrees, is the circuit mainly capacitive or inductive? So if we have an RCL circuit and we calculate our phase angle to be negative 47 degrees, the fact that it is negative tells us that it is mainly capacitive. Okay? And also if we're asked, is the voltage leading or lagging behind the current? So to answer that, we have to look back to Eli the Iceman. Right? So if we know that it's mainly capacitive, we can look right here. And we see that the voltage is lagging behind the current. So in other words, the current comes before, so the current comes before the voltage. So voltage is leading, or here, voltage is lagging, like that. And that's because there's a negative phase angle. Okay? Also, a really important conceptual thing is that energy is never dissipated by inductors or capacitors. So power energy is only given by a resistor. That's just a very conceptual thing relating to this. And to look at an actual problem, let's say in a series RCL circuit, the resistor has 250 ohms of resistance. So R equals 250 ohms. The capacitor has 3.5 microfarads. 3.5 microfarads of capacitance, and the inductor has 0.6 henries of inductance. So 0.6 henries. If there is a frequency of 60 hertz, so F equals 60 hertz or 60 inverse seconds, and the maximum voltage of 150, so Vmax equals 150 volts, find, and then we have to find all these things, A through F. So here are all the equations that we're going to use. So starting with A, we're looking for the impedance of the circuit. So we're looking for Z. Z, we're going to have to just plug in what we know. So take the square root of R, which is 250 squared, plus, okay, and now we don't know what XL or XC are. So to figure that out, we have to use these equations right here. So let's start by finding what XL, the reactance from the inductor, is. So XL equals 2 pi times our frequency of 60 hertz times the inductance of 0.6 henries. So L equals 0.6 henries. Like that. Okay? So let's see what our calculator gives us. So 2 pi times 60 times 0.6, we get 226.2. And this is the reactance, so it's measured in ohms. 226.2 minus whatever XC is. So XC equals 1 divided by, and this is kind of an easy mistake to make. Make sure you do 1 divided by 2 pi times 60 times 3.5 times 10 to the negative 6. Okay. So let's see what our value for that is. So if we take 3.5 times 10 to the negative 6, times 60 times 2 pi, and then do 1 divided by that. We get 757.9 ohms. So again, it's measured in ohms. Okay, so let's write that in squared. So now we have our equation for impedance. We can keep typing this in. So 226.2 minus 757.9 gives us a negative value, but if we square it, let's see, get a huge value. But if we take 250 squared plus that value, okay, gives us another huge value. And if we take the square root of that, we finally get that Z equals 587.54 ohms. Okay, so again, this is measured in ohms, the impedance. Okay, so that answers part A. We've got that out of the way. Now B, find the maximum current through the circuit. To find that, we can relate this to Ohm's law, V equals IR, but we're not dealing with just R. We have to accommodate our equation to this, right? So if we then rearrange this, we get that I max equals V max divided by Z. So I max equals, what did we say V max was? Maximum voltage of 150 volts. 150 volts. Let's see. Divided by 587.54 ohms. So 150 divided by 587.54, we get 0.255 amps. So 0.255 amps. So that is our max current. Okay, so we've answered part B. Let's move on to part C. The RMS current through the circuit. So this is related to a different equation, which is right here. Okay, so IRMS, that's the root mean squared value. Okay, so we have to take I max divided by the square root of 2. And logically here, we're dividing I max, the maximum current, by a number greater than 1. So IRMS should be less than whatever I max is. So 0.255 amps divided by the square root of 2. We get that IRMS is 0.181 amps. Okay, so that was part C. Let's keep moving, see what part D is. The phase angle. Okay, so to find the angle, this angle right here is called phi. We just have to plug in these different values that we have from earlier. So phi equals the tan inverse of, let's see, XL, which was 757.9, or XL was 226.2, so 226.2 minus XC, which was 757.9, divided by the resistance. So the resistance we had is 250 ohms. Okay, now let's punch this in and see what we get for our phase angle. So 226.2 minus 757.9 divided by 250, okay, and then take the tan inverse of that. I get negative 64.8. degrees. So that is our phase angle. Okay. Now for part E, let's find the power factor. So that's given by the equation P equals IRMS times VRMS times cosine of theta. So let's rewrite that. P equals IRMS times VRMS times cosine of our angle. So we calculated IRMS earlier, but we have to calculate VRMS. And that is pretty much given by the same equation. So Vmax divided by the square root of 2. So 150 divided by the square root of 2. Let's see what that is. So after punching that in, I get 106.1. 106.1 volts. Okay, now we can plug that back into here to figure out our power factor. So P equals 0.181 amps times 106.1 volts times cosine of negative 64.8 degrees. So let's see what we get. Okay, so after typing that in, I get 8.17. So this is our power factor right there. And lastly, for part F, find the maximum voltages across each element. So what that's asking for, so what VR is, what VL is, and what VC is, which is given by this equation here. So it's important to note that it says the maximum voltages. So if we're looking for the maximum voltages, we need the maximum current times each of the reactances, like this. Okay. So let's plug that in. What did we say I max was? So for I max, we calculated it to be 0.255 amps. 0.255 amps times 250 ohms goes 0.255 amps times the reactance from the inductor. What did we calculate that to be? 226.2. 226.2 ohms. And lastly, for our capacitor, we had 757.9. Okay, so let's calculate these and find our answers. So 0.255 times 250 is 63.75 volts. 226.2 times 0.255 is 57.681 volts. And finally, 0.255 times 757.9 is 193.27 volts. Okay, so we've answered everything that the question is asked for. I know it's a long problem, but this is how you solve for everything that you can pretty much ask for an RCL circuit. So thank you for watching.